One type of problem that calculus gives us the ability to solve is optimization problems. You may recognize that the word optimization is similar to the word optimal. This is because optimization problems are typically about finding the measurements or circumstances that ensure the best or most efficient outcome in a given situation. Suppose a rancher wants to enclose a field on his property for livestock, and he has materials to build 400 meters of fencing. What should the enclosed field's length and width be in order to maximize the area of the field? This is an example of an optimization problem. The key word here is maximize, since optimization problems usually ask for either a maximum or minimum value. For this problem, we need to know the ideal dimensions of the field. That is the length and width that yield the greatest area for the 400 meters of fencing allotted for the perimeter. Let's take a look at some dimension samples in their areas to get a feel for how the length and width relate to change in area. One way the rancher could build the fence is with a width of 50 meters and a length of 150 meters. This would use up all 400 meters of fencing. With this setup, the rancher's field would have an area of 50 times 150, which equals 7,500 square meters. However, if the rancher chooses to increase the width to 60 meters and therefore decrease the length to 140 meters, the area of the field would then be 8,400 square meters, which is a sizable improvement. If we keep increasing the width and decreasing the length, we will continue to see the increases in area up to a point. Eventually, a maximum area will be reached, and then the area will begin to decrease. For example, if we increase the length all the way up to 199 meters and decrease the width accordingly to just 1 meter, the area of the field will only be 1 times 199, which equals 199 square meters. As we can see, the area of the field very much depends on its dimensions. And there should be a sweet spot, a set of dimensions which maximizes the area of the field. How can we determine exactly what those optimal dimensions are, though? The good news is you won't need to use trial and error for these problems. Before we solve this field problem, we need to talk about critical points. Consider this shape. You may recognize this shape as a parabola, but I specifically want you to notice that this shape has a maximum point right here. We can see pretty clearly that this is the highest point on the shape, but it also has a special characteristic which makes it what we call a critical point. What is the slope of the tangent line at this exact point? Since the line is changing directions from upward to downward, the slope at this exact point is 0, and the tangent line is flat. This would also be true of a minimum point on a curve. At an arc's lowest point, the line will switch directions from downward to upward, and the tangent line will have a slope equal to 0. Points where a function's derivative are equal to 0 are called critical points. Critical points also exist where a function's derivative does not exist, such as points where there are breaks in continuity or when a function has sharp turns. Because of this, we can find minimum and maximum values of a function within particular domains by searching for points where the derivative of the function equals 0 or does not exist. For example, the function f of x equals negative x squared plus 4x is a downward opening parabola. We can find the maximum of the function by taking the derivative of f and solving for the point x, which makes it go to 0 or not exist. Let's start by taking the derivative of f. So f prime of x will be equal to negative 2x plus 4. Since there is no point that would make this undefined, we can set f prime to 0 and solve for x. So 0 equals negative 2x plus 4. We can subtract 4 from both sides to get negative 4 is equal to negative 2x, and then we'll divide by negative 2 on both sides to get x is equal to 2. So the maximum for f of x occurs at x equals 2, and we can plug in f of 2 to see what the height there is equal to. So we'll have f of 2 is equal to negative 2 squared plus 4 times 2. So negative 2 squared is negative 4, plus 4 times 2 is 8, so plus 8 is equal to 4. So this function has a critical point at 2, 4. Let's return to the example of the rancher now. We know that he needs to use all 400 meters of fencing materials, so the perimeter of the enclosed field must be equal to 2L plus 2W is equal to 400, where L and W represent length and width respectively. Area of a rectangle is of course equal to length times width, but in order to find a critical point, we need to write a function for area in terms of only one variable. Let's use L as that variable, and we'll solve for W in terms of L to make the area function. So we're going to solve for W by subtracting 2L from both sides. So we'll get 2W is equal to 400 minus 2L. And then we'll divide by 2 on both sides to get W is equal to 200 minus L. So the area in terms of L equals length times width, or equivalently for the rancher, we'll have A of L is equal to length times the width is 200 minus L. So if we simplify this, we'll get that A of L is equal to 200L minus L squared. Remember, in order to find the dimensions that maximize the field's area, we need to locate a critical point of this function. Let's take the derivative of A now. So A prime of L is equal to 200 minus 2L. We can see that there is no way for A prime to be undefined since there's no possibility of dividing by 0 or having a negative radicand or log argument. Let's then solve for where A prime equals 0. So if we set A prime equal to 0, we'll have 0 equals 200 minus 2L, and we can solve for L by subtracting 200 from both sides to get negative 200 is equal to negative 2L, and then divide by negative 2 on both sides to get 100 is equal to L. There's a critical point when length of the field is equal to 100 meters, which indicates that the area of the field is maximized when the length equals 100 meters, and consequently when the width equals 100 meters as well. The area of the field with these dimensions is 10,000 square meters. Let's work through another example. Find any critical points for the function h of x is equal to x cubed over 3 minus 2x squared minus 12x plus 40. And then determine where the maximum of the function is within the domain x from 0 to 10. To locate critical points, we first need to take the derivative of h. So h prime of x will be equal to x squared minus 4x minus 12. This function won't have any points which cause it not to exist, so let's set it equal to 0 and then solve for x. So we'll have 0 is equal to x squared minus 4x minus 12. We can factor this right side and get x minus 6 times x plus 2. So then we can set both of these equal to 0 and solve for x. So we'll have x minus 6 equals 0 and x plus 2 equals 0. So that gives us x equals 6 and x equals negative 2. Since negative 2 is outside the domain we are concerned with, we can disregard it. So we're left with a critical point at x equals 6. The second part of this problem is finding the maximum point of h of x within the domain 0 to 10. Since we have a critical point at x equals 6, it's very tempting to say that the maximum is there. However, if we check the graph of h, we can see that this isn't exactly the case. In fact, x equals 6 gives us the minimum point of this function. In order to find the maximum, we need to check the endpoints of the domain and compare their heights to that of the critical point. Let's check h of 0 and h of 10 now. Now we can see that the maximum point of the function h of x on the domain x from 0 to 10 is at the point 10, 53.3 repeated, and not at the critical point x equals 6. For this reason, anytime you have an upper and lower limit for x in an optimization problem, make sure to check those values against the critical point to find the true maximum or minimum. Let's do one more example. Lisa is working on a geometry project and is making shapes from pliable metal wire. She has 8 feet of wire that she wants to cut into 2 separate pieces. With one piece, she will make a circle, and with the other, she will make a square. In order to maximize the total area of the circle and square, how long should the piece of wire for the square be? Or will Lisa have the greatest area by dedicating her wire to only one of the two shapes? Since we are trying to maximize area, we need to come up with a formula for area. This formula needs to be written in terms of only one variable so that we can take its derivative and find a critical point. Let's choose the variable to be the letter x, representing the length of the wire used for the square. We know that the area must include the circle's area as well as the square's, so a of x will look something like this. So the area of our figure will be equal to the circle's area plus the square's area. The area of a square is equal to its side length squared, and the side length of Lisa's square will equal 1/4 of x. So the square's area will equal 1/4 x squared, which is 1/16x squared. So let's plug that in for our square's area. We'll have a of x is equal to the circle's area plus 1/16x squared. To get the area of the circle, we need to realize that the length of leftover wire from the square will equal 8 minus x feet. This will make up the circumference of Lisa's circle. The circumference of a circle equals 2 pi r, and the area of a circle equals pi r squared. So let's get the value of the radius by dividing 8 minus x by 2 pi. So our radius will be equal to 8 minus x over 2 pi. Then we can square this and multiply by pi to get the circle's area. So we'll have a of x is equal to pi times 8 minus x over 2 pi squared. And then we'll add the square's area, which we found to be 1/16x squared. We can simplify this a little bit, and we'll have 2 pi squared will be 4 pi squared, but one of the pi's will cancel out. So our numerator will stay 8 minus x squared, but our denominator will be 4 pi. Then we'll add 1/16x squared. Before taking the derivative, let's FOIL out the numerator of the first term. So we'll have a of x is equal to 64 minus 16x plus x squared, all over 4 pi. And then over here, I'm going to put x squared in our numerator, so plus x squared over 16. To find the derivative of the first term, we could use the quotient rule. However, since the bottom is simply a constant, we can just factor it out and take the derivative of the top. So a prime of x will be equal to 1/4 pi times the derivative of the numerator, which will be negative 16 plus 2x. And then we'll take the derivative of this part of the function, which will be x over 8. This derivative doesn't have the potential of dividing by 0, having negative radicands, or negative log arguments, so we won't find anywhere that it does not exist. Let's instead solve for where it equals 0. So we'll take this function and set it equal to 0, and have 0 equals 1/4 pi times negative 16 plus 2x plus x over 8. And we're going to solve for x. So this will be 0 equals, if we distribute 1/4 pi, we'll get negative 4/pi plus x over 2 pi plus x over 8. Then we can add 4/pi to both sides. So we'll have 4/pi is equal to x over 2 pi plus x over 8. So we can solve for common denominators, and we'll have 4/pi is equal to 4x over 8 pi plus pi x over 8 pi. Then we can add these two fractions. We'll have 4/pi is equal to 4x plus pi x over 8 pi. Then we can multiply by 8 pi on both sides. When we do that, our pi's will cancel out over here, and we'll be left with 32 equals, these also cancel out, so equals 4x plus pi x, and we can factor out an x on the right side to get x times 4 plus pi, and we can divide by 4 plus pi on both sides to get x is equal to 32 over 4 plus pi. So this is approximately equal to 4.5. And x equals 4.5 is a critical point on the area function. This indicates that Lisa would cut roughly 4.5 feet for the square shape, leaving around 3.5 feet for the circle shape. Remember, even though we have found this critical point, we also must consider the endpoints of the domain. In this case, we should check what the area would be if Lisa used 0 feet of wire for the square, using all 8 feet instead for the circle, and what the area would be if she used all 8 feet for the square and 0 for the circle. The total area if Lisa uses all the wire for the circle will be equal to approximately 5.093 square feet. The total area if Lisa uses all the wire for the square will equal 4 square feet. If Lisa cuts the wire at the critical point and dedicates around 4.5 feet to the square, she will have a total area of approximately 2.24 square feet. It seems that Lisa will have the greatest area if she dedicates all 8 feet of wire to the circle. Whenever you see the words maximize or minimize in a calculus problem, these are signals to indicate an optimization problem is at hand. The first step in solving these is writing a formula for what is being optimized, which is usually area, volume, cost, or profits, in terms of only one variable. Then take the derivative, look for critical points, and test these against the endpoints of the domain to find the true maximum or minimum. This may seem like a daunting process at first, but with some practice, you'll have the hang of it. Thanks for watching, and happy studying!